Okay, now note that in the first two examples, the given functions were differentiable on the entire real number line. For such functions, the only critical numbers are those for which our derivative is equal to 0. In this next example, we have a function that has two types of critical numbers, those for which our derivative is equal to 0, and those for which f is not differentiable. So here in example 3, it says find the relative extrema of f of x is quantity x squared minus 4 to the 2/3 power. We are going to take that derivative, f prime of x. That's going to be equal to 2/3 times our quantity, x squared minus 4 to the now negative 1/3 power. And then the chain rule says we have to take our inner function's derivative. The inner derivative there is going to be a 2x. So if I multiply my fraction by the 2x, I'm going to get a 4x over 3. And this term here with the negative exponent will get dropped down to the denominator, and the exponent will become positive. So we're going to have an x squared minus 4 down there to the 1/3 power. So let's see here, when our numerator is equal to 0, is the whole function will equal 0. So if we set just the numerator, 4x equal to 0, we get a critical number of x equals 0. And let's see when we have a rational expression here for our derivative. Remember, when our denominator equals 0, bad things are going to happen. So if we just focus in on the denominator, the coefficient doesn't matter, the exponent doesn't matter, but what's going on here in the parentheses with the exponent? If what's in the parentheses becomes 0, the entire denominator zeroes out and the function is non-differentiable. So if we just look at as what in the parentheses, x squared minus 4, when does that equal 0? Well, that's when x squared is equal to 4, and if we square root both sides, we'll get a positive and negative 2. So x equals 2 and x equals negative 2 are a couple numbers we want to keep in mind here. These are the numbers, the critical numbers, that are going to chop our number line up into intervals. And our problem does not give us left and right endpoints of the intervals, so we assume it is the entire real number line from negative to positive infinity, and these are the numbers that are going to partition that off. So our first interval will go from negative infinity to 0, or excuse me, negative 2. And then from negative 2, we'll go to our next critical number of 0. So from negative 2 to 0, and then from 0 to positive 2, and then from positive 2 all the way to infinity. So we are chopped up in our intervals now. We want to pick out some test points, one in each interval, and plug those into the derivative to see if our derivative comes out to be positive or negative. Okay, on our first interval, a good number to pick would just be negative 3. That negative 3 goes into the derivative, and it comes out as a negative answer, less than 0, and that means across that interval our function is decreasing. From negative 2 to 0, we can pick out negative 1 as our test value, plug that into the derivative, we get a positive output, and that tells us our function is increasing. On the next interval, we plug in 1 as our test value, we get a negative output from our derivative, and we know that across that interval our function is decreasing. On our last interval, we can plug in a positive 3. Our derivative does turn out positive, and that tells us our function is increasing. So let's apply this first derivative test. Our first critical number was here at negative 2. On the left side, our function was decreasing. We hit negative 2, and then after that, our function is increasing. So we're at the bottom of a valley. That tells us that this is a local min. Our next critical number was 0. On the left side, we were positive. On the right side, we went to negative, and that tells us we were at the top of a hill, or that this was a max value. And our last critical number was at positive 2. On the left, we have a negative derivative. On the right is a positive derivative. So we know, again, we're at the bottom of a valley, and this positive 2 valley is a minimum. And if we want to check out the graph of this function, make this a little bigger. Here's our graph. The first thing we did is took our derivative and set that equal to 0, or found where it was undefined, where our function is not differentiable. And we got 3 values. Negative 2, at 0, and at positive 2. So that is what chopped up our number line from negative infinity to negative 2, and then negative 2 to 0, from 0 to 2, and from 2 to infinity. And then we tested points out to see, in our first interval we used negative 3. So when we tested this point, we found our derivative was negative. We knew that portion of the graph was going downhill. When we plugged in negative 1, we got a positive derivative. Our tangent line has a positive slope at that point. We know our function was increasing until we hit x is 0. And then when we plugged in our test value of positive 1, we got a negative derivative. We knew we were going downhill. And then from 2 to infinity, we were back to a positive or increasing function. Now here in example 4, well, it says when using the first derivative test, be sure to consider the domain of the original function. In this next example, we're given this function, a rational function. Always beware of rational functions because you can have your denominator 0 out, and that is not part of your domain of the function. So this function is not defined at the x value of 0. This x value must be used with the critical numbers to determine our test intervals. So before we even derive it, look at the function. If you see a rational expression, we know that it is not defined at x is 0. So that is a number we're going to use to chop up our intervals, but we're not going to have a min or a max there because, of course, our function is not defined at that x value. So it says here, find the relative extrema of this function. So before we derive it, we could derive with the quotient rule, but I notice I have a 2-term numerator, a single-term denominator. I'm going to break my fraction up into 2 separate terms, both over the same denominator. And now I can simplify. X to the 4th over x squared is x squared, and I can rewrite the second term as x to the negative 2 power. So that is just my f of x rewritten. And now we can derive it a little simpler. F prime of x. F prime of x is going to be 2x minus 2x to the negative 3rd power, and I'm going to rewrite that as 2x minus 2 over x to the 3rd. And our usual operation here is to take the derivative and set it equal to 0 and factor the left side. Well, as it stands right now, we can't factor that left side. Let's get that looking like a single fraction. So here my denominator is 1. I need a common denominator, which is going to be x to the 3rd. I'll multiply through by x to the 3rd over x to the 3rd. And I will get 2x to the 4th minus 2 all over the common denominator x to the 3rd. And remember, we're still setting this equal to 0. This is our derivative. And now I can factor that numerator a little. I can pull out a 2. So I'm going to be left with an x to the 4th minus 1. And then my x to the 3rd in the denominator. That numerator is able to be factored even farther. If I look in the parentheses, I see that x to the 4th minus 1. That's a difference of perfect squares. So I can break this down into an x squared plus 1 and an x squared minus 1, which that term is another difference of squares. So I can factor this single term down into an x plus 1 and an x minus 1. So x plus 1, x minus 1. This is all still over our denominator of x to the 3rd, and we're setting it equal to 0. Now we look to the numerator. When any of those factors, we have 4 things multiplied together, when any of those equals 0, our numerator equals 0, and therefore the whole function does. The coefficient we don't have to worry about. Our first term here is something squared plus something more. That will never equal 0, so that term we don't have to worry about. But when x plus 1 equals 0, we know that x equals negative 1 is going to be a critical number. When this last term, x minus 1 equals 0, we know that when x equals positive 1, we also have a critical number. You know, we could look at the derivative and say, oh, well, that denominator equals 0 when x is 0, and that would be a critical number, but that's overridden by the fact that the original function is not defined at that value, so we're not going to have a derivative there at all. So here are the 3 numbers that are going to chop up our x-axis. We found these 2 are critical numbers when our numerator is equal to 0. And this x equals 0, remember that is from the original function. We are not defined at x is 0 at all. So let's move on to our test intervals here. And our first interval is going to be from negative infinity up to negative 1. and then from -1 to 0. Our third interval goes from 0 to 1, and our last interval from 1 to positive infinity. Now we just want to pick out some test values, plug them into the derivative, and see what the value of our derivative is, positive or negative. So first, our test value, I'm going to pick out a -2 here. When that -2 goes into the derivative, it pops out a negative answer. And that tells us our function is decreasing. Between 0 and -1, I'll plug in a -1/2. And we're going to get a positive output from our derivative, which tells us our function is increasing. From 0 to 1, we can plug in +1/2. Our function will give us a negative output. Our derivative function will give us a negative output. And we know our function is decreasing. And our final interval, we can plug in a +2. The derivative will give us out a positive value, which tells us our function is increasing. Now let's think about that first derivative test. Here, 0 is not a critical number. Our function was not defined at 0. Don't look at this and think, oh, it was increasing and then decreasing, so we have a max there. We are not defined at that because our original function was rational. Our denominator would zero out at that x value. But over here, we have a critical number of -1. On the left side of it, we were a decreasing function. We hit -1, and then we turned to an increasing function. So we know here we have a local min. This is a min value, the bottom of a valley. Here at the critical number, +1. We went from decreasing on the left to increasing on the right. Again, we have another valley going on here, so that critical number has to be a minimum value. And let's take a look at the graph of this function. Here's our original function with our denominator x squared. So when that is 0, we know the function is not defined. We have an asymptote there. And we set our derivative equal to 0, and we found critical numbers at +1 and -1. So we knew something was going on at these points on the graph. And then we did our first derivative test, and we went from an decreasing to an increasing function, so we know that is a relative min, and the same at +1. On the left, we were at a negative derivative, or a decreasing function. On the right-hand side, we went back to an increasing, so that is also a relative min.